Now we're going to talk about saddle point asymptotics, which is the process of refining saddle point bounds to get the more accurate estimates that are available to us. So again, in the previous segment, I talked about the basic idea of using Cauchy coefficient formula to just find the saddle point, use a circle of radius equal to the saddle point, and just bounding the integrand everywhere on the circle with its value at the highest point. But now what we're going to do to get better asymptotics is to just focus on the place near the saddle point. As we saw early on, the integrand is really low for most of the circle. So what we want to do is find a good bound on the tail, or the part that's really low, and focus on the part of the path that's near the saddle point. This is like Laplace's method that we talked about very early on in asymptotic analysis, where you focus on the center, bound the tails, and then bring the tails back. And with that kind of calculation, we can get very accurate asymptotic estimates. That is, we're going to look at the little part of the circle that is close to the saddle point, and then the rest of it we're going to show to be negligible with different estimates. That's the saddle point method. And it's easy to see how it's going to be effective, because we saw that the bounds were off by square root of 2 pi n, which is essentially the part of the circle, it's low, and we were assuming it to be high. That's all it is. It's a different factor. So we're going to do a little more analysis to see that we don't need to do that, and we can get an accurate estimate with Laplace's method. Now, this, as with many of the transfer theorems that we consider in analytic combinatorics, there's going to be technical conditions that need to be satisfied for us to apply this method. And just for completeness in this lecture, I'm going to call that susceptibility. That's just a name for the technical conditions that are going to be needed for saddle point approximations to work. All it is really some kind of formal statement that this process is going to work, so that you can find the saddle point, and that's the root of the saddle point equation, and the curve can be split into two parts such that the tail part is negligible, and that the part that's not negligible is the saddle point. That is, there's a quadratic approximation, just like we saw from just an elementary analysis of what a saddle point is. So it doesn't have to be precisely a saddle point, but if it's near a saddle point, you have that quadratic approximation. That's as general the conditions as we can make them. And as with many of our transfer theorems that we considered earlier on for singularity analysis and other approaches, these technical conditions have to be checked. If there's a multiple saddle point, then maybe there'll be some other part of the condition to worry about, but I'm not going to worry about that in the lecture. And also the tails have to be negligible in the first place, and then however this estimate works, it has to be negligible to bring the tails back. And we'll look at a detailed example, but this kind of technical detail is more appropriate to read about that in the book. So what this is going to lead to is the so-called saddle point transfer theorem. And all it says is, if you have a contour integral, and we write it as f of z equals e to the f of z, e to the little f of z, just to simplify the calculations a little bit. If no singularities, there's no problem with doing that. So if that's susceptible to the saddle point approximation, then the integral is approximated by f of zeta over that square root of 2 pi factor. It tells us exactly how to compute that missing factor. This is a general technique for contour integration. It's not just for asymptotics. That's about any contour integral. It gives a way to approximate it. And the proof is very similar to the proof that we did for the saddle point bound. So that's the theorem, but what we want to use it for is a transfer method for a generating function. So just translating that over to our use of Cauchy's theorem, where we're looking for coefficient of z to the n in a generating function, then what we want to do is just apply this theorem with g of z, with f of z equals g of z over z to the n plus 1. So so that's all that is plugging into the general theorem, f of z equals g of z over z to the n plus 1. So our saddle point equation is just modified slightly, and the main point is that we evaluate our function at the saddle point, and then we have this corrective factor, which is just square root of 2 pi times the second derivative. So it's a plug and chug method of getting coefficients of z to the n out of entire functions that have no singularities. Now, there certainly is technical detail in proving susceptibility, and I'll try to illustrate some of that in an example, but in this lecture, what I really want to focus in on is the idea that this kind of approximation is available. I can't claim that this is as clean as many of the other transfer theorems that we've looked at, because checking those technical conditions can be more challenging. So anyway, the summary is that for our generating function g of z, and this is just doing the math backwards, we're going to use the saddle point equation, g prime of z over g of z equals n plus 1 over z. So that's zeta is the solution to that. And then solving that, that's the approximation, where little g is log of big G minus n plus 1 log z. That's a relatively simple calculation for getting asymptotic estimates of coefficients. So let's go back to our examples. So estimating 1 over n factorial as a saddle point approximation, coefficient of z to the n and e to the z. So g of z equals e to the z, and so then taking logs, our saddle point equation is 1 minus n plus 1 over z equals 0. So that's zeta equals n plus 1. And then the saddle point bound is just plug in zeta. Second derivative is 1 over n plus 1. So the approximation that we get is e to the n plus 1 over n plus 1 to the n plus 1 square root of 2 pi over n plus 1. And again, that one goes to 1 over e, and just simple asymptotics gives us exactly Stirling's approximation, e to the n over n to the n over square root of 2 pi n. So this extra factor in the saddle point approximation gives us the extra factor that we were missing before. So the choice that we always have when using saddle point is you can do all the detailed calculations to check that the integral is susceptible and so forth. Or you always have the option of just using the bound and sacrificing that factor, which certainly in many applications people will choose as an option. It becomes important to get the factor. We can get it, but it takes some work. And again, checking susceptibility, you have to check that the tails are negligible, that the central approximation is quadratic, and then we can complete the tails back in a reasonable way. And that's really doing the calculation for the particular function that we have. So at this level, we don't necessarily have the general schema, but this is an important starting point for limiting distributions. That is something advanced that we don't study in this course. Let's just look at, and again, this is the last lecture in a long course, so I'm not going to do these calculations in detail other than to just exhibit them. This is the kind of calculation that's needed to show that it's susceptible for this problem. What we're doing is trying to do the contour integral for e to the z over z to the n plus 1, or just putting it all in one function, z minus n plus 1 log z, around this circle, z equals n e to the I theta. First thing is to just switch to polar coordinates, z equals n e to the I theta, and you just plug that in there, and most of it comes out, the e to the n over n comes out, and all that's left is integral 0 to 2 pi e to the n e to the I theta minus 1 minus I theta. That's just a simple substitution. So now what the saddle point method requires is that we're able to split it into two contours, one for a little part close to the saddle point, and then the rest for the tail, which is all the rest of the circle. Those are the two contours, and the point is we have to be able to prove that for the tails it's exponentially small, and that you can look at the text for that proof, but when we're away from the saddle point, remember in the 3D diagram, that's when the curve drops all the way down, exponentially small. And then in the part close to the, so we're going to just neglect the tails and just work with the part close to the saddle point. Another thing to notice is that if we can slightly shift the saddle point if we want, it simplifies the calculations quite a bit, as long as we have that quadratic approximation near where we are. So now we're just focusing on the central part of the integrand, and e to the I theta minus 1 minus I theta, well, it's minus theta squared over 2 plus theta cubed. Just expand e to the I theta, subtracting off the first terms. The leading term left is the quadratic approximation that we're talking about. By restricting theta 0 to be less than a certain value, then we can drop the big O term and get an approximation of our integral as long as, say, theta 0 is n to the alpha with alpha less than minus 1/3, then we can drop the big O term. And there's a small calculation to check that. And then we can change variable and do the integral, and that's the integral that we have. And then we want to restrict theta the other way to complete the tails so that we can get an integral that we can evaluate. And then that integral is a regular normal integral, square root of 2 pi n, 2 pi over n is the final result. And so we had to bound alpha one way to complete the tails and bound it the other way to drop the O term. And we're left with finding a value in between minus 1/2 and minus 1/3. So we pick n to the 2/5, and that's the complete derivation that shows that it's susceptible to saddle point. And again, these are intricate calculations, but it's kind of always the same. And it's a matter of where that bound is, and that depends on the function. There's a place where the estimate near the saddle point is accurate, and there's a place where the tails are negligible, and just have to find that place. And then in the end, we're getting Stirling's approximation back for this problem. So that's an illustration of the difficulty of proving susceptibility, and unfortunately that's still there for many problems. Again, this transfer theorem is not at all as simple as others that we've looked at. And you might well ask, well, you're talking about the difference between n to the 2/5 and n to the 1/2. That's about n to the 1/10. wasn't there something in early lectures about this not being relevant unless n is so huge that we wouldn't care about it? Is that a problem here? Well, actually, it's not, because in these cases we're talking about estimates that are in the exponent. So n doesn't need to be. So if n is like 1 billion, then these estimates are still something that we're going to care about and are going to matter because it's in the exponent. The other thing is that I'm doing a quick illustration here. We can get full asymptotic series to any desired precision using these methods. And also, when we get the answer out, we can validate them numerically, which we usually do for problems of this sort. And we're still pushing towards the goal of having a general schema that'll cover whole families of classes. It's hard to say that we're as far along on this goal for saddle point as we are in some methods, but actually when you look at the extension to limiting distributions, we actually are. But that's an advanced topic beyond the scope of this course. So let's look again at the transfer for the central binomial case. So now we're estimated coefficient z to the n and 1 plus z to the 2n. So that's our g of z. So if we take log of g of z minus n plus 1 log of z, and then define that to be our function for the saddle point equation. First derivative is 2n over 1 plus z minus n plus 1 over z. Second derivative, and then saddle point equation is set that one to 0. So the saddle point is n plus 1 over n minus 1, and that's what we saw before. And so the approximation says plug in n plus 1 over n minus 1 into this formula. And we get a pretty ugly equation that we can go ahead and estimate. But remember, it's okay to shift the saddle point. And you want to simplify the calculations. And this one is really close to 1. So rather than go through an estimate of those, let's just use 1. So if we say the saddle point is 1 and plug it in to this equation, then we immediately get out for the n over square root of pi n as expected. Making that choice early on also simplifies the check of susceptibility and so forth, which is something you want to do. You're going to slightly shift the saddle point as long as that doesn't disturb the idea that you have a quadratic approximation and that you have negligible tails. It's not going to matter, and we can more easily complete a full derivation for a problem like this. So again, another approach is to just use the saddle point bound and sacrifice the square root of pi n factor. But then if it's an application where it's important, you can see what that factor is, and then if you need to prove it, you can go in and do it using standard techniques. I think that's the message. So that's saddle point asymptotics.